Continuing our look into how magnetic fields can be used in real-world applications, here's an important piece of analytical equipment that's used by physicists, chemists, and biologists to understand what materials are made of. So it's used for things like carbon dating, where we want to know how much C12 and C14 there is in materials, and it can also be used for things like protein characterization. Let's start off by getting the maths out of the way. The mass spectrometer creates a charged beam. Now it could be ions from whatever material we're trying to analyze, or it could be a beam of electrons. But we get this straight beam. Then what we're going to do is use a magnetic field to bend that beam, to make it move in a circle. And we're going to use the radius of curvature of the circle to determine what the material is. So if we're going to make the charged beam move in a circle using a magnetic field, we're going to supply a magnetic force to it. And that force is given by F equals BQV. And that is going to be equal to the centripetal force to keep it in circular motion. So that's F equals mv squared over r. This gives us BQV equals mv squared over r, or BQ equals mv over r. And that rearranges to Q over m equals V over BR, which is still a lot of unknowns. We don't know Q, we don't know m, and we don't know V. So it's not going to work at the moment. What we need to do is to find out V, and we're going to do that by filtering out some particles. And we're going to do that with a component called a velocity selector. As the name suggests, the velocity selector only allows particles with a certain velocity to pass through, with all other particles getting blocked. It works by using magnetic and electric fields with opposing forces. In this diagram, I have placed an electric field pointing up by placing a positive plate at the bottom. If positive ions are fired through here, they will deflect upwards with a force given from E equals F over Q equals V over D, so F equals QV over D. If I also put a magnetic field in, so the North Pole is at the back and the field direction points towards us, then with current going left to right and the left hand rule, we get a downward force given by F equals BQV. So the two forces are opposing. If they are equal, the ion will be undeflected. If they are not equal, the ion will deflect up or down. So if we put some barriers here, only some particles get through. So mathematically, this is when QV over D equals BQV, or V over D equals BV, or small v equals BV over D. Since B, V and D are all constants, we can control their values and select which value for velocity, V, can get through. It's a velocity selector. Plus, we know the velocity, which is handy for the next part. In this part, we want to detect the particles. We already have the equation from before, Q over m equals V over BR, and now we know V and B, and we can easily measure R. So we now have a detector to measure Q over m, but we wanted a mass spectrometer really, not a charge to mass ratio spectrometer. Well, we're actually a bit stuck there, but it doesn't matter, because remember that the purpose of these machines is to find out what something is made of. Let's say it contains two elements, Material A has a mass of 2, material B has a mass of 4. They both get charged randomly, meaning that some ions have 1 charge, some have 2 charge, some have 3 charge. This means that the set of Q over M for material A is 1 over 2, 2 over 2, 3 over 2. We might expect the peaks proportions to be like this, with most of the ions having Q over M of 1 over 2. The set of Q over M for material B is 1 over 4, 2 over 4, 3 over 4. So there is some overlap, but we can tell the difference. This means that almost every time we can use mass spectrometry to tell us the composition with very high confidence. Sometimes the results are uncertain, but that's life. And that is the mass spectrometer. It has a source of charged particles at the start, which is going to be a cathode producing electrons via thermionic emission for A level. The electrons are accelerated through a known voltage, giving them all the same kinetic energy equal to EV. There's a velocity selector that uses orthogonal electric and magnetic fields to allow only electrons with the chosen velocity through. There's another magnetic field that detects the electrons with a radius of curvature dependent on the charge to mass ratio, as given by the equation E over m equals V over Br. In conjunction with Milligan's slightly dodgy oil drop experiment that determined the elementary charge, we now have a way of determining the mass of an electron. If instead we used ions for this, then we have a way of finding out the composition of a piece of matter.